What I really wanted to showcase today was basically how to do rapid feature engineering and how to basically go from raw data, like you have a transaction data set, and how to start engineering features, prototyping very quickly, and then actually serving them in production.
For quick background, Justin is the ML platform lead at Doppel, where he fights social engineering using ML, phishing attacks, identity theft. Before that, worked at Level, processed 100,000 credit card transactions a day, and built the core fraud detection models there. And we're going to learn today how to build similar stuff, right? So maybe tell us, what are we going to learn today, Justin?
Sweet. Yeah. So what I have on the right is basically a Jupyter notebook, and I've already gone ahead and loaded in some data. And so basically I've taken some data sets from like a Kaggle competition, and I've sort of tweaked it and added in a little bit of fixture data myself. But effectively we have like a data set of transactions. And so just to show what that looks like, we have like a time series of, you can imagine like credit card transactions, and there's a bunch of entities on this data, right? So there's like a customer or like a client, there's a card, there's a merchant, there's some other sort of scalars in the data set like the amount. And yeah, so pretty simple data set with just like a couple entities. And you can imagine like we've normalized out the schemas, and so we have like a data set for like the members or the clients, we have a data set for the merchants, and then we also have like a data set of merchant category codes, which basically just like codify categories of spend that a merchant might have. And so with just this raw data, what I want to show is basically how we can start engineering features right away and how we can start developing on top of this. And so imagine the problem statement is something like you're given all this raw data, you have some card program that you're basically owning, and you want to like make authorization decisions, so approval or denial decisions in a couple hundred milliseconds. And so what I have on the left is, on the left we have feature schemas. So these are basically one-to-one with the schemas from the data frames on the right. And so yeah, we have like a merchant category code feature class, a merchant class, a transaction class, and I'm leveraging like Python Chalk's SDK right now. And so basically by adding this little features decorator on top of the classes, that enables me to spell out all of the features under the all of the attributes under the classes features basically. And so in Chalk, there's really two core concepts. The first is feature classes, and so I've just talked through that. The second is resolvers, and so resolvers basically tell you either how to go out and get the data or how to resolve the data effectively. And so here I've already pre-written out like a couple SQL resolvers. This is going out and connecting to like a data warehouse that I have, where I have like a few tables under like a data set. And so yeah, this is again like one-to-one pretty much with the schemas that you're seeing like from the notebook. And so all of these are basically features that I'm resolving. And so with Chalk, there's basically two special comments that I need to add. One is like the underlying source, and so here the source is just pointing to like the data warehouse that I've set up. And then next is the feature class that I'm resolving. And so for the transactions SQL query, I'm resolving the transaction feature class. For the merchant SQL query, I'm resolving the merchant feature class. And I haven't done any feature engineering yet, right? And so these are all just like one-to-one. And so sweet, this is sort of our jumping off point. And so one of the first things I might want to do once I've set these up is basically start developing in a local branch. I don't want to clobber maybe like our production feature store. I just want to develop on the side, and when I'm ready, then I want to push to production. And so Chalk has this concept of branches. Right now it takes a couple seconds just for the server to start, since it's been a few minutes since I've developed. But effectively this just takes like the set of features and resolvers that I've codified, and it should only take a couple seconds, and it basically applies it to the branch namespace that I've spelled out. So I'll give it a couple seconds. In the meantime, maybe I'll also just start developing some features. So one of the features that I might want to do is like a really simple one, and I might want to just like, these categories are messy. I might want to do some simple normalization and like lower the category. Chalk has some built-in like accelerated functions. And so what I'm doing over here is basically leveraging, and I can show it in the UI, like they have a pretty rich set of functions across all the different types of scalars. And so right now I'm just leveraging like this sort of accelerated C++ implementation of like a preprocessing function, which is just lowering a string. And they have a pretty rich set of functions that they support. Sweet. And so then another feature that I might want to have is like whether a merchant category is in a block list. And so in this case, I might codify out that feature. And then what I'll want to do is actually start implementing like how this feature gets resolved, right? And so I might have like a set of merchant category codes already. And so then what I'll want to do is basically spell out like is MCC in block list, and I'll have like an implementation which basically just checks if this MCC at inference time is in like a block list. And so this resolves the new feature that I just set up. Okay, so let me just quickly go into the UI and check what is up with the branch server. Okay, so the branch server is started up. And so one thing I might want to do just to quickly illustrate is like what a query looks like. So I have some, basically I want to spell out like some input features, and I want to see what features I get out as output. And so here I might pass in like a merchant category code that I know about, 5813, and then I want to see what I get out as output, and I want to spell out the branch that I'm testing on. And so yeah, this takes a couple seconds, but it's actually going out, pushing down a filter to BigQuery. So first let me actually apply the changes, and then I should be able to run that query. So this takes a couple seconds basically, but under the hood it's like packaging up my code, spinning up a container, pushing it out, and deploying my changes to my branch. And then if I run this query, let me see, so it's saying it can't find, so let me actually just comment this out really quickly just to see what this looks like. So merchant category code, let me just try to look at the category. Okay, sweet. And so it basically pushed down a filter for the ID 5813, because that's the only ID that I care about. It went out to BigQuery and it executed that SQL resolver. And so I can actually go into Chalk's UI to see what that query looks like at runtime. And so it's basically doing something very simple, right? It's just going, the sort of starting point is BigQuery. It executes this like SQL resolver that I have, and it's pushing down a filter and returning the results. So I can also do this just to illustrate across like a batch of inputs. And so I can pass in a couple merchant category codes if I'm interested in seeing like what the computed features look like. So I'll just pass in a couple merchant category code.id, and then I just have to supply this bulk argument, and this should basically return like 3 rows for those same 3 merchant categories that I passed in as input. Sweet, and so I got that. Okay, and so now I actually want to go back to this feature that I've just implemented and get that working. So yeah, I want to check if the merchant category code is in a block list. Sweet, and so what I'll have as input is, okay, so what I want as input is the merchant category code ID actually. So this interface is a really specific one. So basically I'm saying I want to pass in like the ID, which is the code of the merchant category, and that'll help me resolve basically whether the code is in the block list, because it'll basically just do a contains check. Okay, so with this I should be able to like apply my changes again. It'll take a second, and then I can query like for those exact same features. So this time I'm just going to query the entire feature class for the given ID that I had. And yeah, I'd expect this to return like true for is MCC in block list. Sweet. And so I got that. And I can also see the accelerated function is working. And maybe also just to illustrate what this looks like in terms of Chalk's like query plan that it dynamically generates under the hood, we can see this is a little more sophisticated than the one that I had last time, right? And so it's evaluating the SQL resolver, it's doing like that push down filter, but then it's actually taking the Python like UDF that I had, and what it's doing is it's parsing the Python AST and actually transpiling this into like more accelerated C++. And so yeah, it's actually significantly more optimized and it skips the GIL. And so and that's effectively what runs to then compute like the final set of features that I want. There's also this expression that I added. Sweet.
And Tristan, real quick, just explain when you say skipping the GIL, you mean the Python's interpreter lock. So just explain that part real quick.
Yeah, so with Python, it can be pretty slow. There's this mutex called like the GIL, the global interpreter lock, which basically bottlenecks your concurrency. It only lets one thread execute at a time for memory safety. And so part of Chalk's secret sauce is they can basically at runtime, ahead of time, basically look at the UDFs that you've defined, understand the sort of the dependency graph in all the expressions that are codified within that UDF, and transpile that into something much more optimized, I think under the hood in C++ or something, to actually enable true parallelism. And so you really start to reap the benefits of this, both like online, like, so this is actually like an online query where I'm passing in a given merchant category code ID, and I want like all these features right now. But also actually helps a lot at scale offline. You can imagine if I have like 1 billion transactions and I want to compute all these features historically, you'd get really bottlenecked if this was just like an expression in pure Python and you had to like run it row by row. And so this basically with Chalk, like they optimize this, they enable true parallelism, and it actually enables significant speed ups both offline and online.
Wow. So you can get great performance with Chalk, better than like an older feature store.
Yeah, exactly. Yeah. Cool. So I'll keep going, and yeah, we'll get to sort of more sophisticated features. So I might want to do the exact same thing basically with merchant names. And so I'll also have like some simple pre-processing and like a merchant block list feature. These are pretty like standard typical features that you might have when you're doing feature engineering for like a fraud detection use case. And so then I'll go ahead, and you can imagine like the pattern looks pretty similar for the merchant use case, where the interface is I'm passing in like a given merchant ID and I want to check whether or not it's in a block list. And so again, I can like apply it to my branch, and I can actually speed this up, and I can basically, there's like this watch argument that I can supply, which will basically just keep watching for changes. So maybe let me actually do that. So if I supply this watch argument, basically now anytime I make file changes to my resolvers or to my feature sets, it'll automatically go and deploy that code, package it all up, deploy it, and then I can basically just start writing queries. And so I'll do that, and I'll open up like a separate tab in the terminal. So that code all just got deployed. So let me try just quickly testing this out. So I want to pass in like a sample merchant ID. I'll just take a random one, and I want to see sort of what the merchant features for that look like. Oops. Okay, so I need to do Chalk query. So then this should spit out something pretty similar to like the merchant category code feature class. And so yeah, I can see it isn't in the block list. The ones that I'd blocked were just like some dummy numbers, and it's also lowering the merchant name. So we're getting faster now with the features that we're developing. Cool. And so I have this transactions feature class. One of the interesting things that I can do, like Chalk really tries to enable you to model like the richness of features and like the relationships between features. And so I can actually point to other bags of features within like a given feature class. And so I might want to model like the merchant category code. So let me add merchant category code. And then I even have like a member sort of feature class below this. So I'll add that, and I'll just like do some forward type hinting since I haven't defined that up front yet. And so what this actually lets me do is reference all of the other features that I just defined across like the merchant category code, and the member. And so all I'm doing is I'm spelling out like the join relationship. And so each transaction has like one merchant, has one merchant category code, and has one customer or member. And so I'm just spelling out like it's a one-to-one join, and I'm spelling out basically what the foreign keys are. So the merchant ID, like the primary key of the merchant, maps to the transaction merchant ID. The merchant category code ID maps to the transaction MCC feature. And then like the member ID, like the primary key of the member feature class, maps to the transaction client ID. And so now like one interesting thing that I can do, since I've defined these foreign keys and these join relationships, is to actually compose like sort of higher level features based on the ones I've already defined, right? And so maybe a simple interesting one might be to check whether for the given transaction that I have, so like someone goes out and swipes their card, and at inference time I want to know like was the merchant category code or the merchant on a block list. So sort of like a composition of those two features. And so what I can do is MCC, so I'll just define the feature, MCC or merchant and block list. And this autocomplete is pretty nice. Basically there's this accelerated sort of chalk expression that I can leverage, and I can just show that in the UI really quickly. So they have this if then else conditional expression, which basically again is like much more optimized. So instead of sequentially evaluating or like serially evaluating each condition in the expression, it's actually evaluating them in parallel. And so you can imagine again, like at inference time or even offline, this is going to be significantly faster. So it's actually an underscore expression. So just to also maybe quickly step through like the syntax here, since it can be a little bit terse sometimes. In this expression, basically the first argument is the condition. The next argument is the condition if it's true, and then the last argument is sort of the value you want the feature to have if it's false. So here I'm basically leveraging these this sort of underscore syntax to point to like the merchant object, and then I'm indexing into that like is merchant and block list feature, and then I'm just basically checking, is that true, or is the merchant category code in the block list. So again, like this should have already automatically been applied since I'm watching for feature changes. And so one cool thing that I can do is I can test this out. So I'll test it out on one of the transactions, maybe in the data set. I'll just take a random ID like this first one, and I want to look at this specific feature, and I want to do it on my branch. Sweet. And so for this transaction, like the merchant ID is 59935, which isn't on the block list. The MCC is like 5499, which isn't on the block list. And so it returns false. And if I look at this query plan that just got generated, again, also a pretty simple one, but you can actually see, so it's doing the same thing. So it's evaluating that SQL resolver. It's pushing down a filter for the input ID that I specified. It's evaluating that accelerated Python, that function, that UDF I defined, which checks like whether or not the MCC tied to that transaction is in a block list. And then it evaluates that optimized expression I just spelled out, right, which checks whether the MCC or the merchant is in the block list. Cool. So, I realized actually what I want here is, this is right. Yeah, merchant and merchant category code. Okay, cool. And so we can start to get even more sophisticated. And so one thing that I might want to do is like normalize the amount. The amount, let's see, in like my transactions data frame, if I just like try to plot it out, I might need to import. So I expect this to be like sort of a right skew distribution, right? So large majority of the transactions are for only a couple dollars, and then there's like a long tail of super large transaction amounts. And so I might want to normalize this and take like the logarithm of that. And so Chalk also has like an expression for doing that. That's one simple feature I might have. And then maybe, I'm also processing like reimbursement requests for my card program. And so when someone submits a reimbursement request, they write a memo that actually like describes what the transaction was for. And maybe in my authorization sort of business logic, I want to actually check if that memo is congruent with basically like the merchant that tied to that reimbursement. So maybe I'll do some pre-processing on the memo, and then I want to actually take an embedding of it. And so here, again, like terse syntax, but it's all like sort of baked into Chalk and pretty intuitive. And so the idea is I'm taking an embedding where the input is actually like this pre-processed memo that I have, this memo string, and I want to make a call out to like one of the OpenAI embedding models. If for some reason the string is empty, or there's like an error trying to grab the embedding, it'll just default to like a sparse vector of just like zeros. And so, cool, this should have already been applied. And so this time I want to get out a few features. So I want to see what the memo, maybe I want to see what the memo looks like. I want to see what the pre-processed memo looks like. And then I also want to see what the embedding looks like. So memo embedding. Cool. So I'm passing in that same transaction ID, and I'm spelling out I want these like 3 other features as output. And so we'll wait, give this a sec to run. Sweet. And so we can see I've actually like hard coded a memo just for like this toy data set. And so the memo is actually the same for every transaction, but you can imagine like you might have custom memos. But we can see it's lowercasing it, and then it's actually taking an embedding of the lowercase string. And if I look at the generated query plan for this, we can see same sort of thing, right? So it's going out, evaluating the SQL resolver, evaluating the expression, and then evaluating the embedding. Cool. And so maybe like one interesting sort of feature, and then we can get to like what it would actually look like to have like a model on top of these features, is I want to also take like an embedding of like the merchant name and the category, or some combination of that. And then I want to take do a dot product with that embedding and the embedding of the memo, and see if there's any similarity. If there's like low similarity, then maybe that's like a sign that I should flag that reimbursement for review. If it's like high similarity, then maybe that's like a good signal. And so one thing I might want to do is like combine merchant and MCC. And so here I'll have like a string expression which is grabbing like the merchant name, it's grabbing the category code, and it's just combining the two, right? And so if I try to see what this looks like for a given transaction, I can just spell that out. And like these, the merchant name and the category code category like aren't actually on the transaction. I'm leveraging like the join relationships to actually go out and find what these values are. So that's sort of the key difference with this feature. Sweet. And so it'll take a second, and so I'll keep going, but basically I want to then take like an embedding of that, right? So I'm referencing that feature. Sweet. And so it just came back as well. So the first part is the merchant name, the next is the category. So I want to take an embedding of that, and then the next thing I want to do is also take like the cosine similarity of the two things. And so Chalk also has an expression for cosine similarity, and so here the first argument is just like the embedding of the memo, then the embedding of the merchant and the merchant category code, and I want like a cosine similarity. So I expect this to be like a similarity score from 0 to 1. So then if I go and run this again, this time I think I can I'm lazy, so I'll just put the entire transaction object, and so I want to get like all the features back for this given ID. And so this will take a sec to run. But yeah, I'd expect basically like all these features on the transaction to get populated in this output. Part of the slowness here might also be just because I'm leveraging like my data warehouse BigQuery instead of like a relational DB like Postgres. But cool. So let's see. The feature that I wanted was like this memo merchant cosine similarity. I can see it's like it's sort of just in the middle, like 0.5, but it's basically looking at the merchant and MCC embedding, it's looking at the memo embedding, and then it's computing like a dot product and computing the cosine similarity. Sweet. Maybe one other quick thing just to talk through before I go into like showing what like a model could look like is I showed an example of like a one-to-one join, right? So like a transaction has a member, a merchant category code, but maybe I'm interested in modeling things at the member grain. So here I want to say like a member has many transactions, right? And so Chalk has their own abstraction of a data frame, which is a little bit functionally different than like a pandas because it's lazily loaded versus like eagerly executed, and so sort of just different semantics, but they have their own abstraction of a data frame, but conceptually it's pretty similar. Here I'm just saying like instead of a has one, there's a has many relationship between a member and a transaction, since one member can have many transactions. And then maybe I want to feature like the max transaction amount over that data frame. And so again, like I can write a query where I pass in, this should already all be applied, like the member ID, and so I'll just come and grab a random one. So 506, or 10, let's see. So member ID equals 10, and I want to get out all the transactions that member has. And so this might be a little bit more expensive, like member might have thousands or hundreds of thousands of transactions, but same sort of underlying concept under the hood. Okay, so this might have been a little bit too large to return. But yeah, under the hood, this is sort of the same concept where it's just going out and grabbing like all those transactions. So maybe let me just comment this out, and let's actually like try to build a resolver where, you know, on a transaction I want to have like a predicted fraud score, and I want this to be a float, and I want this to be taking in like a bunch of the input features that I had, and I want it to spit out like a fraud score probability. So I can go and write like an online resolver. I want to predict the fraud score. I want to take in, let's see, like a couple different features. So one might be like the cosine similarity of the memo and the merchant. The next one might be the transaction amount. The other one might be like whether the merchant or MCC was in a block list. And then as my output, I want to get like this fraud score that I'm spelling out. And so, cool. So what I'll want to do is first construct, let's say like so you can imagine I might have like a trained model artifact where I'm like learning some weights for those features. But under the hood, basically I'd have something like this, right? Where I have like a couple different features. So here I have a couple different features that I want to train a model on. I learned some weights around those features. I need some labeled data to learn those weights. But then all I'm doing is taking at inference time like a dot product of those features and those weights, and then I'm normalizing it to get a probability from 0 to 1. So sweet. So let me actually try to see what this might look like for like a given transaction that I have. So I want to get this like predicted fraud score. Oh, okay. So maybe let me just try applying this really quickly. Okay, so I had an invalid feature. Let me look at that. Okay, so it hallucinated a feature. So let me come back and just spelled it out incorrectly. So it's MCC or merchant and block list. So now if I apply, I think this should fix it. Sweet. So it applied it to my branch, and then I can rerun. I can rerun the query that I had to see what the predicted fraud score might look like. And then we can actually go in and inspect the query plan, and we'll see something a lot more sophisticated than what we originally had at the very beginning. So part of the magic here is actually that Chalk is like orchestrating all of the feature computation under the hood. I just have to declaratively spell out like what I want as output, but I'm not actually saying anything about all the intermediate features. Chalk is basically under the hood like constructing some dependency graph and figuring out like what I need exactly at the moment that I need it, right? And so if I click into the query plan, this actually looks a lot more sophisticated than what we had originally. And just maybe to quickly talk through it, so we have our underlying data source, which is like my data warehouse in BigQuery. I have this SQL resolver, which basically tells me where the raw data is. I'm passing in a transaction ID, and so it goes and evaluates like a pushdown filter and executes that SQL query. And then I have a bunch of sort of raw sort of like intermediate features that I'm computing, and then I'm applying. So like one of them is like whether the thing is in the block list, merchant category code's in the block list. The next is like the memo. I'm grabbing like embedding of the memo. I'm taking an embedding of like the merchant and the merchant category code. I'm evaluating this expression. And then it actually finally evaluates like the Python resolver that I just cooked up, which takes in like a few of those features and spits out a fraud score. And so that's an example of like what online inference might look like. And this could actually be anything. So this could be like a network call to like some Cloud Run service or something where I'm hosting like a model endpoint, inference endpoint, and I can make like a network call to that and just like pass in like the features that I have at inference time. In this case, it's sort of just like a toy example where I'm hard coding the weights, but you can imagine this might be like an actual model artifact that I'm loading in. And so maybe the last thing that I wanted to show was just like, I've showed a couple examples of like online inference. So it's where I have like sort of a single row, like a single input that I'm doing inference on. And I can do this like at really large and a high scale throughput if I want to. The other sort of use case is right now I'm actually in development. And so I've just like written up all these features, but I actually want to see what it would look like, what the performance and like predictions and the feature values would look like historically. And so I've sort of written an example of what that might look like with Chalk as well. And so here I have like an offline query, right, where basically I want to do the same thing. I want to pass in like a transaction as input, and I want to get out as output. These are just a couple of the features that I had from before. And so if I evaluate this, here I'm just running this function on like 20 sort of rows of transaction inputs. We can actually see what this would look like. So under the hood, this is actually going and evaluating like an offline query. So let's see. And it just went out, this is at 10:43, it just went out and basically generated all the computed feature values on like the historical data that I passed in. So what we see here is pretty interesting. We see like some of the outputs, so some of the sort of scalars of like whether the merchant or MCC is in the block list, the embedding values. We see some like empirical stats over the data that I just like wanted to run the backtest on. One of the arguments that I actually spelled out was like a dataset name. So you can imagine if I'm in an org with like 10 other data scientists and we want to leverage like some of the features that other folks have developed, we might actually have a strong use case to share features, even though I'm just like developing in my own branch. So I can spell out a dataset name, and that effectively enables anyone else in the org to leverage like the same computed features for their own use cases. They might want to train their own models, and like we might want to do a bake-off to see who has the better model. They might want to leverage those features for their own use cases. And so just by passing in that one argument, like with a few lines of code now, anyone else in the org can go and basically take all the features that I've generated and use it for their own use case. And so this is an example of like what an offline sort of query might look like if you're training models offline, or doing some back testing before you actually go and productionize these features online. Cool. So that's pretty much what I had. Overall, what we talked through was really just how to go from like raw features to like increasingly sophisticated engineered features to finally like a dummy model where we're taking those features that we generated, some weights that we've learned maybe from like a model that we've trained, and generating like a fraud prediction score. And then I've shown like how you can do inference online and offline as well.
This is very cool. And one thing that's interesting is that like there were feature stores before Chalk, but Chalk seems like there's two things really well. One is the parallel processing of the features. The other is making the dependency graph for you. So you
Yeah.
just have to write less boilerplate. And the dev experience looks really smooth. That like, am I missing anything? How is because there were so many products doing this, and Chalk is clearly like solving it really well. At previous companies, what did you use, and what how's your experience been using Chalk compared to those?
Yeah, no. So at Level, I did a lot of this actually myself. And so what the process we didn't really have any vendors that we were using. We did a lot of this in-house. And so we it was extremely painful. It was like months of development time. We developed our own sort of internal abstractions of like what features look like. We built our own like online feature store. I would do like exploratory data analysis offline in Python, and I'd generate all these like really interesting features. I'd train a model, but then it would be way too slow for inference. At Level, we had our own sort of transaction processing system, and we were making like real time credit card authorization decisions. So like the budget for like fraud detection or like our risk component in that broader system was only like 200 milliseconds. And so there's no way I could do that with just like the features that I cooked up in Python. And so I'd basically transcribe all of them into Go. And so we had like a model as a service pattern, have to basically generate like a new feature pipeline for my online inference. I'd have to be really careful to make sure there was no like data leakage and that I was like engineering things the exact same way I'd done it offline. I'd even have to like transcribe features from Python to Go and make sure they're available at inference time. And so overall, just like super arduous process. Took months really to go from like idea to production. Yeah, at the time we weren't fortunate enough to have like a vendor like Chalk, but with Chalk, and have used them a lot at my current company. The dev experience is like I would say almost like 100x, where I can go from like idea to production in like hours. I don't have to worry about like maintaining separate feature pipelines. I don't have to worry about how to compute all the features if I have like a bunch of intermediate features. Chalk handles all of that. It's super composable. With a simple like query, I can backtest everything super quickly. I can also do it for online inference, and so it's just like 100x like devx improvement.
Yeah, very cool. And like, how about the costs involved with something like this? I assume you're paying the feature vendor, but and you're also paying BigQuery. But do you think about that at all? Is that something people listening should be thinking about?
I think it comes into play when you're doing this stuff at scale. And so at Level, we were doing this at scale. We were processing like hundreds of thousands, like millions and tens of millions of dollars of credit card transactions every day. My current company, we're dealing with like even larger scale, like internet scale in terms of like domains that we're ingesting every day. And so Chalk has two sort of offerings. One is like a self-hosted offering, and the second is like a hosted offering. But basically, if you're like in an organization, you can deploy this within your own like sort of infrastructure. And so I'm using them specifically right now, like hosted on GCP. And so then it's just like the compute cost that I'd otherwise be using myself if I was to like generating all these features at inference time in like my own sort of cloud run service or something like that. All I'm really doing is leveraging Chalk to orchestrate the generation of that feature. So that compute cost I would have had otherwise. But then there's also like a platform fee on top of that for using. So that's roughly like the mental model of how to think about like the cost for something like this.
Makes sense. And how about in the future with LLMs? Do you think there's a world where we use LLMs to figure out what new features to build for our models? Like, how does that work? Is that even the right way of thinking about the future of feature engineering?
Yeah, I think that's definitely like a use case that's proliferating that I'm seeing at least in my current organization. I think the bottleneck is at least right now, it's just like feature generation latency latency. And so if you're making like network calls like to some provider to generate like features, and maybe you have like unstructured data, like here in this case we had like a transaction memo, and maybe you have like other really rich features on a transaction, and maybe I want to like use like an LLM as a classifier and like pass that transaction in, that's transaction string in, and like get like a prediction from an LLM if it's fraudulent or not, and get some reasoning from it. If I only have a budget of a couple hundred milliseconds, then I might be out of luck to like make that network call, because that network call might take a couple seconds. But if I have like more relaxed latency constraints, like I have a lot more time, then that actually starts to make sense. And so I think it makes a lot of sense like offline. I've leveraged LLMs pretty heavily as like judges to almost like a sanity check against like the scores that I'm generating like in real time. Use like LLM as a judge offline and do some like offline analysis. And it really depends on the use case. I think over time I expect like inference latency to go down, especially if you're using like quantized versions of these models, or even maybe like self-hosted like smaller versions of these models. So it would be an interesting feature to see like what it actually looks like if you can generate like LLM inferences at like a couple tens of milliseconds or something like that.
Yeah, interesting. So today you use LLMs to like judge whether a feature is working well or not.
Yeah, almost like a sanity check. Like you can imagine with something like a fraud detection use case, you almost have some sort of like operational budget every day, right? So you're making all these you're making like hundreds of thousands, millions of decisions on like actual users swiping their card out in the real world. There's going to be some misclassification. So some things you're incorrectly blocking, some things you're incorrectly approving. And generally you have some operational arm of the org, which is then like reviewing these things, making sure that, there's no like nefarious behavior. And so one thing you can do is like, if I have like LM as a judge offline, is I can run some job maybe in like an hourly cadence and like flag like the most egregious disagreements between like my LLM and like the prediction that I made at inference time. And then I can like surface that to like someone from ops. So that's like a simple example of how you might go about like that.
Right. So basically to replace the human in the loop in feature auditing.
Yeah. That's the promise of it. Yeah.
Cool. And if you were joining a new company today, how would you structure your first month? Let's say you were doing similar stuff and you're building some model to like detect fraud, or maybe it's detecting something brand new. But how would you structure your first like month on the job? What are the things you would prioritize doing first? Let's say you're starting from scratch.
Yeah, if you're starting from scratch, and that was literally like the case for me at Level, like where we started with no card program, we built all this internal infrastructure and business logic, and then basically started running a card program. The most important thing is to think really carefully, I think, about your data models, right? Because you want those to be intuitive and extensible, composable over time, especially as you evolve your system. So for example, at Level, it wasn't just a credit card program. We accepted like reimbursements, we accepted claims from providers, because really one credit card for all your benefits. And so we needed a data model that was extensible. So that's one thing I would think really carefully about. I think the other important part is just like getting labeled data, especially for these sorts of use cases, like with credit card transaction fraud. One of the salient features is that there's like a fundamental class imbalance. 1%, maybe even just a few basis points of the transactions that you're processing are actually fraudulent. Needle in the haystack problem. And the one thing you'll want to ensure that you have set up really early on is some sort of feedback mechanism to get that labeled data. And so in fraud, like a traditional way you might do that automatically is by looking at transactions that ultimately get disputed by the customers that you have. Another way that you might do it is by having someone like on the operational side who can like review some set of some queue that you're curating of suspicious transactions. Another way you might do that is by like having some feedback with like your actual customers, and like you ping them or call them if you see something suspicious. A lot of the traditional like banks, like a JP Morgan, do this. Like if I go right now and swipe my card at a casino, it'll get blocked and I'll get a call from JP Morgan. So feedback loops is super important. And then I think leveraging like a platform like Jock potentially basically to like make the development super quick, because that's the most important thing these days, just like velocity.
Yeah, makes sense. And I know you managed a bunch of people, right? Like at Level, I think it was 6 engineers. you were working with on the platform team. When you interview other ML engineers or people who want to build ML platforms, what do you look for? Like, what would you say that the key skills are?
Yeah, I wore a lot of hats there: data science, engineering, product. I think, yeah, fundamentally you're looking for like really strong system design skills and like really solid engineering chops. I think like these days that profile, maybe you need less of certain specific skills of like if they've done it before, if they've like what sort of tools they've used, since you have a lot of vendors out there that do this now automatically. But on the ML platform side, I think like you want folks who have designed systems at scale for like real production use cases, like this one that we talked through, like credit card transaction fraud, where you have to design like really low latency, high throughput systems. I think that's in a world where you can sort of the implementation, like execution of like code generation part is super easy. The more important thing I think is like systems thinking and ability to like reason about sort of maybe novel problems that you're engineering systems around.
Right. And so deeply understanding the data model at the company is probably, it sounds like that's something you would suss out in an interview.
Yeah, I think that's an underrated one. Like it's not something a lot of people intuitively maybe think about. Maybe like a lot of people join companies where that's like already established and they don't have to think really critically about like the underlying data models. But if you're building something from 0 to 1, that's probably one of the most important pieces.
Yeah, makes sense. Thanks for sharing all this. Anything else you want to share that could be useful for people?
No, yeah, I think if you're just getting started, I think everything you could want is available online. But the best way, in my experience, is to really just like get your hands dirty, play around with data sets on something like a Kaggle, maybe even try to develop your own like inference service with like a model that you train, then you host and deploy. That's really the best way to sort of build out this skill set, I think.
Awesome. And if people want to get in touch with you, what's the best way for them to do that?
Yeah, you can reach out on LinkedIn. Also active on X as well, so you can feel free to DM me there too.
Amazing. Well, Justin, thank you for sharing this. This was really interesting for me. Hope it was interesting for other people. And
Thanks, Eli.
all right, guys, that was Justin.
Yeah.
Bye.